They removed the air, every single molecule of it. Pumped out, evacuated, gone. And then in the silence of a near-perfect vacuum, a train flew. Not on wheels, not on rails, not on anything physical at all. It floated, it accelerated, and for the first time in human history, a superconducting maglev vehicle inside a vacuum tube crossed 623 kilometers per hour, shattering a world record that had stood for years. Welcome back to the channel. What you are about to witness is one of the most audacious, most technically complex, and most consequential engineering undertakings ever attempted in the history of ground transportation. It is called flight. It is real. It is Chinese, and it may change the way every human being on Earth moves between cities forever. This is not just a fast train. This is not just an upgraded version of something that already exists. This is a fundamentally different category of machine, a vehicle that travels not through air, but through the absence of air. A train that is also, in almost every meaningful engineering sense, a spacecraft that never leaves the ground, a system that borrows from rocket science, from aviation, from quantum physics, from materials engineering, and fuses all of it into a tube buried in the earth of northern China. Imagine the fastest commercial passenger aircraft you have ever flown on. A Boeing 737 cruises at roughly 850 kilometers per hour at altitude. Now imagine a train, a ground vehicle, something with passengers, something you board at a station reaching speeds that approach that, not in the sky, not at 35,000 feet, on the ground, inside a sealed tube, in a desert in Shanxi Province. That is what flight is designed to do. And the engineering challenges standing between today's prototype and that future. They are not small. They are not incremental. They are the kind of challenges that have broken billion-dollar companies, humbled world-class engineering teams, and convinced serious people, very smart, very experienced people. So before we talk about what China built, we need to talk about why nobody else could. The idea of traveling through a vacuum tube is not new. It is not a product of the 21st century or even the 20th. In 1799, more than 2 centuries ago, an English engineer named George Medhurst imagined a pneumatic transport system, a capsule driven through a sealed tube by differences in air pressure. He wrote about it, he drew it. He could not build it, but the seed was planted. In the 1840s, atmospheric railways trains pushed by air pressure differentials briefly appeared in Britain and Ireland. They worked imperfectly for a few years. Then they failed. The seals leaked, the leather valves rotted. The engineering of the era could not hold. Then came 2013, and Elon Musk, in the summer of that year, Musk published what he called the Hyperloop Alpha White Paper. It was 57 pages. It proposed a system connecting Los Angeles and San Francisco, a 560-kilometer journey in 35 minutes at speeds approaching 1,200 kilometers per hour inside a near vacuum tube. The estimated cost, $6 billion. The world went electric with excitement. Dozens of companies formed almost overnight. Virgin Hyperloop One raised hundreds of millions of dollars. Hyperloop Transportation Technologies promised lines across continents. Universities built student pods. Governments commissioned feasibility studies. The race was on, and then slowly, painfully, expensively it collapsed. Virgin Hyperloop One shut down in December 2023. Despite raising more than $450 million across nearly a decade of operation, the company never secured a single commercial contract, never built a line, never carried a paying passenger. The technical problems proved harder than the pitch deck suggested. The business case never closed. The money ran out. This was not a failure of imagination. It was a failure of engineering reality, meeting financial gravity. And it left a vacuum, an ironic vacuum, in the global race toward this technology. Now, to understand why China succeeded where the West stumbled, you need to understand what the actual problem is. Because it sounds simple. Take a tube, remove the air, put a floating train inside, go fast, But every single word in that sentence conceals an engineering nightmare. Start with the tube itself. A hyperloop system connecting two major cities does not need 2 kilometers of tube. It needs hundreds. Eventually, thousands. And that tube must be airtight. Not airtight, except for a few small leaks. Perfectly, continuously, hermetically sealed across its entire length, at every joint, through every temperature cycle, through every vibration, through every ground shift, through every season. Consider what temperature does to a metal tube. Steel expands and contracts with heat. A tube 600 kilometers long, exposed to the temperature swings between a Chinese winter and a Chinese summer, will expand and contract by hundreds of meters across its length. Every joint that moves is a potential leak. Every leak is a cascade failure. The moment the vacuum breaks at any point, the pressure wave that races through the tube at the speed of sound is not a minor inconvenience. At the speeds T, flight is designed to travel. It is catastrophic. Then there is the air resistance problem. This is the reason the vacuum matters in the first place. A conventional high-speed train, even the best ones China currently operates, the CR400 series capable of 350 kilometers per HR, spends the vast majority of its energy fighting air, not friction between wheel and rail, air. At 350 kilometers per HR, aerodynamic drag accounts for roughly 70 to 80% of total energy consumption. At 500 kilometers per HR, it is even more dominant. Physics does not negotiate. The faster you go, the harder the air pushes back, and it pushes back with a force that grows with the square of velocity. Double the speed, quadruple the drag. This is why no conventional train, no matter how aerodynamically optimized, no matter how powerful its motors, can reach 1,000 kilometers per HR above ground. The air will not allow it. The energy requirements become physically and economically impossible. At those speeds, you are not fighting air resistance. You are fighting a wall. Remove the air, and the wall disappears. In a near vacuum, even a partial one, with air pressure reduced to just a small fraction of atmospheric drag, drops to almost nothing. The train does not need to push through anything. It glides. It flies. The only limits on its speed become the strength of its magnetic system and the precision of its guidance. But removing the air creates its own problem. A near vacuum tube is not inert. It is under enormous stress. Atmospheric pressure, the weight of all the air above you, 10.3 tons per square meter at sea level, is constantly pressing inward on every surface of that tube from the outside. Build a tube 3 to 4 meters in diameter, pump out the air inside, and each meter of that tube must resist tons of inward force. Do this for hundreds of kilometers, and you need an extraordinary amount of engineered strength, distributed perfectly without a single weak point. The West tried to solve this with solid metal tubes. Precision, engineered expensive, heavy metal. The cost per kilometer was staggering. The manufacturing complexity was enormous. Each section had to be machined to extremely tight tolerances, transported to site and joined with seals capable of maintaining vacuum for decades. It was effectively trying to build a pipeline to the standard of a spacecraft fuselage. It did not scale. The economics never worked. Then there is the magnetic levitation itself. Standard maglev, the kind powering Shanghai's existing urban maglev, which reaches 431 kilometers per HR, commercially works on principles established decades ago. Electromagnets create lift by attracting or repelling against a guideway. It is elegant, it is fast, but it has a ceiling. The reason is energy. Conventional superconducting maglev systems require the superconducting coils, the magnets themselves, to be cooled to temperatures close to absolute zero, using liquid helium or liquid nitrogen. This is expensive, complex, and operationally demanding. Every meter of guideway, every onto magnet must be maintained at temperatures colder than deep space. And even with all of that, the world record for a superconducting maglev on a conventional open track held by Japan's SL0 series, the most advanced maglev train ever built, was 603 kilometers per HR. a number achieved in 2015 in a test tunnel without passengers, a number that had not been broken in nearly a decade. Until February 2024 in Datong, Shanxi Province, northern China. But let us not jump ahead, because before the record, before the tests, before any of this was possible, there was a blank canvas. At first there was only desert, no track, no tube, no facility, just the flat, dry, dusty expanse of Shanxi Province in northern China, a landscape defined by coal mines, lowest plateaus, and the kind of dry, freezing winters and blazing summers that make precision engineering outdoors a particular kind of misery. Datong is not a glamorous city. It is not Beijing or Shanghai. It is an industrial city, historically dependent on coal, located in a province with limited international visibility. But it had something the project needed: flat land, relative geological stability, political support from the Shanxi provincial government, and critically distanced from the complexity of urban infrastructure. In 2022, construction began at the Datong test facility. This was not a small undertaking. Before a single tube segment could be installed, the ground had to be surveyed with extraordinary precision, not the kind of survey you do with a GPS unit and a clipboard, the kind of survey that uses laser interferometry, ground-penetrating radar, satellite positioning accurate to millimeters, and geological bore samples to understand exactly what is beneath the surface at every point, because the tube must be straight, not approximately straight. Not straight within normal construction tolerances, straight within margins, measured in fractions of a millimeter over its entire length. A kink in the track that would be invisible to the naked eye, a deviation of a few millimeters over 100 meters, translates at the speeds t, flight is designed to travel into lateral forces that would tear apart the guidance system, defires the vehicle, and create vibrations that propagate through the entire structure. Every millimeter mattered. The ground preparation team spent months on survey work alone, mapping subsurface geology, identifying zones of differential settlement, places where the ground might compact unevenly under load and cause one section of tube to sink faster than another, installing monitoring instruments in the earth to track ground movement in real time, establishing a grid of reference points so precise that any movement of any part of the system, at any point in the future, can be detected and corrected before it becomes a problem. Then came the foundation work, and this is where the Chinese team made their first major departure from the Western Hyperloop engineering approach. The teams led by Master Engineer Xu Shengqiao at the China Railway Engineering Consulting Group and the broader engineering collective working under CASIC's direction refused to accept the premise that a vacuum tube had to be a metal tube. The cost of metal tube fabrication, transport, and installation at the tolerances required was prohibitive. It would make the economics of a commercial system essentially impossible. So they invented something new, a composite structural system using N-shaped beams, a cross-section shaped like the letter N that integrated a steel outer shell with vacuum-sealed concrete infill. Inside the concrete, a network of epoxy-coated rebar and glass fiber reinforcements. Glass fiber, not conventional steel rebar. Because steel rebar inside a magnetic system creates eddy currents, parasitic electromagnetic fields that bleed energy out of the propulsion system by substituting glass fiber reinforcements where possible. The team cut these energy losses by more than a third. This was not a minor refinement. This was a structural innovation that changed the cost equation of the entire project. By manufacturing these composite beam sections in controlled factory environments and then transporting them to site for assembly, the Chinese team cut construction costs, according to the published engineering papers, by approximately 60% compared to the conventional all-metal approach. 60% on a system where the tube structure represents a dominant fraction of total cost. That is the difference between a technology that is theoretically possible and one that is economically deployable. The tube sections arrived at site on flatbed vehicles. Each one was lifted into position by heavy cranes, operating on precision, graded working platforms, set down onto pre-installed foundation systems. Addiate, using laser-guided positioning systems, aberrate to fractions of a millimeter. Then came the joining, the sealing of each section to the next. The joints are where conventional Hyperloop designs historically failed. the seal must be perfect. It must stay perfect through thermal expansion and contraction. It must stay perfect through ground vibration, through maintenance operations, through the pressure cycles created every time a vehicle passes through. The Chinese team developed a multi-layer sealing system for the joint, a primary inner seal, a secondary outer seal, and a monitoring layer in between a thin space instrumented with pressure sensors that continuously report the state of the joint to the central control system. If either seal begins to fail, the monitoring layer detects the pressure change immediately. The system does not wait for a failure, it predicts one. Then came the interior of the tube, because what you are building is not just a sealed container. You are building a precision-engineered environment, a controlled, instrumented, active system that must maintain specific conditions across its entire volume at all times, regardless of what is happening outside, along the inner walls of the tube. The engineers installed the guideway, the track that the T-flight vehicle does not touch, but interacts with magnetically. This guideway is not a rail. There is no physical contact. It is a precisely arranged array of electromagnetic coils that when energized in carefully sequenced patterns, create the magnetic field that both lifts the vehicle off the surface and propels it forward. The coil arrays are continuous along the entire length of the tube. Each coil is individually addressable. The control system can energize any coil at any power level, in any sequence, in real time, allowing the vehicle's position, speed, and trajectory to be managed with extraordinary precision from a central control facility. Between the guideway coils and the tube wall, the engineers installed the sensor network, thousands of fiber optic strain gauges, embedded in the tube wall material, monitor the structural state of the tube in real time. Temperature sensor, pressure sensors, vibration monitors, acoustic sensors that listen for the specific frequencies associated with seal degradation, structural cracking, or anomalous resonance. This is not passive monitoring. This is a living nervous system, a network that samples the state of every significant point in the structure thousands of times per second, feeds that data to AI-driven analysis systems, and triggers responses, magnetic speed reductions. Within milliseconds, the AI-driven magnetic dampers are themselves a significant engineering achievement. As a vehicle moves through the tube at high speed, it creates aerodynamic disturbances, pressure waves, turbulence, even in a low vacuum environment. It also creates vibrations in the tube structure. Conventional engineering approaches deal with vibration, heavy structures, isolation mounts, damping materials. These work up to a point. At flight speeds, they are not enough. The magnetic damper system works differently. Instead of absorbing vibration passively, it actively opposes it. Each damper is a controlled electromagnet. The fiber optic sensors detect a vibration beginning to develop a wavefront forming in the structure. The AI system calculates the precise counter force required to cancel it. The damper activates, applies that force, and the vibration dies before it can amplify. This happens continuously across the entire length of the tube, thousands of times per second. Without it, the vibrations at operating speed would amplify into resonance, structural resonance that could, at extreme cases, destroy the tube. With it, the vehicle glides through an environment that is dynamically almost perfectly still. The vacuum system itself required equally careful engineering. The tube is not pumped to absolute zero pressure that is neither achievable at scale nor necessary. The target is a low vacuum environment, a partial vacuum that reduces air pressure inside the tube to a small fraction of atmospheric. Even this partial vacuum provides a dramatic reduction in aerodynamic drag in normal conditions above ground. A vehicle faces approximately 15 psi of air pressure resistance at speed. Inside the low vacuum tube, that figure drops to close to 1 psi, a reduction of roughly 93% in air resistance. To achieve and maintain this, vacuum pumping stations are installed at intervals along the tube. Each station houses industrial-scale vacuum pumps, redundant power supplies, automatic valve systems, and local monitoring equipment. The stations are interconnected. If one fails, adjacent stations can compensate. The system is designed to maintain vacuum levels continuously, even when a vehicle is passing through, even when maintenance is occurring on a section of tube. The airlocks at each end of the tube where vehicles enter and exit require their own engineering chapter. A vehicle cannot simply pass from atmospheric pressure into a near vacuum without an intermediate step. The airlock must allow the vehicle to enter, seal behind it, pump down the airlock to match the tube's vacuum level, open the forward door and release the vehicle all in a matter of seconds. The reverse happens at the other end. This is in miniature exactly the same challenge as a spacecraft airlock. It is not coincidental that CASIC China, as largest maker of missiles and spacecraft systems, is the organization running this project. The institutional knowledge required to solve this problem already existed inside the company. And then, on a cold morning in February 2024, it was time to test what they had built. The vehicle, sleek, enclosed roughly the dimensions of a small train carriage, was loaded onto the guideway. The airlock sealed. The vacuum pumps ran. The monitoring systems confirmed all sensors nominal. Tube pressure within parameters. Guideway coils ready. Vehicle systems nominal. The propulsion sequence began. The electromagnetic coils energized in sequence, a magnetic wave sweeping along the guideway, pulling the vehicle forward. The vehicle rose superconducting magnets on its undercarriage interacting with the coil array below, generating the repulsive force that lifted it 22 centimeters above the surface. 22 centimeters of clear air between the train and the track. No contact, no friction, no wheel squeal, no rail vibration, no mechanical connection of any kind. It accelerated, not gently, not gradually. The acceleration of a maglev system driven by high-temperature superconducting magnets in a near vacuum is a different category of experience from any acceleration most humans have felt. The magnetic wave sweeping along the guideway does not slow. The train chases it along the 2-kilometer track. The T-flight accelerated, guided, and then decelerated back to a controlled stop. The speed reached confirmed by CASIC exceeded 623 kilometers per h-hour. It smashed the previous world record for superconducting maglev trains, held by Japan SL0 series at 603 kilometers per h-hour, which had stood since 2015. The previous record had held for 9 years. China broke it on the first serious public test run, but the speed record, as extraordinary as it is, was not the most important thing that happened in February 2024. The speed record was the headline. What mattered more to the engineers was the data. Thousands of data streams captured from the sensor network embedded in the tube walls, from instruments on the vehicle itself, from the vacuum monitoring system, from the guideway control computers. Data that told them the vehicle tracked its theoretical trajectory. The suspension was stable, the vacuum held, the braking was controlled and precise. The magnetic damper system worked as designed. This was not just fast, this was validated. The verification came in a peer-reviewed paper, published in the Chinese journal Railway Standard Design, co-authored by master engineer Xu Shengqiao and colleagues from the China Railway Engineering Consulting Group. The paper called the test, and this is a direct characterization from the authors, an international milestone, as the first integrated validation of a superconducting electrodynamic suspension system, targeting speeds of 1,000 kilometers per h in a low vacuum environment, successfully demonstrating multiple mission critical technologies at the systemic level, not a component test, not a simulation, not a scale model, an integrated system test vehicle. Guideway, vacuum tube, control systems, emergency protocols, all working together. All validated simultaneously. The engineering community around the world paid attention. The CEO of Hyperloop, an American competitor, publicly acknowledged it, China's recent success with their T-Flight high-speed maglev system. He said, is a clear demonstration that Hyperloop technology is not a distant dream, but a rapidly emerging reality. But the February test, remarkable as it was, still had one important caveat. It was not conducted under vacuum conditions. The tube in February was at atmospheric pressure. The 623 kilometers per h record was achieved with air inside the tube, which meant one thing: the hardest test was still to come, because running a maglev at high speed in air is a challenge. Running it in a near vacuum is a different problem entirely. The vacuum changes everything: the aerodynamics, the thermal management, the acoustics, the behavior of every seal, every sensor, every control system. In a vacuum, there is no air to carry heat away from hot components. There is no air to dampen acoustic resonances. There is no air to provide a medium for conventional pressure sensors to operate in. Every assumption made by standard engineering assumptions so deep, they are baked into the material properties of every component. The design of every seal has to be re-examined for a vacuum environment. The teams went back to work. Through the spring and early summer of 2024, the Datong facility underwent intensive preparation for the vacuum test. The vacuum pumping systems were installed and tested. The tube seals were inspected, tested, re-inspected. The airlocks were commissioned and trialed without a vehicle. The pressure cycling operations run hundreds of times to verify the seal integrity. The pump, downtimes, the valve seating. Emergency protocols were drilled. What happens if a seal begins to fail during a test run? What happens if the vehicle needs to make an emergency stop inside the vacuum tube? What happens if the power fails to a section of guideway? Every scenario was modeled. Every response was tested. Every team member was trained. And on the 22nd of July 2024, the vacuum test began. The T-flight vehicle entered the airlock. The outer doors sealed. The pumps ran. The monitoring system's fiber, optic sensors embedded in every joint, every wall section, every component of the tube watched. Pressure dropped. The airlock reached target vacuum level. The inner door opened. The vehicle moved into the tube. In the silence of near vacuum, the train flew. It levitated 22 centimeters above the guideway. The Omni-G superconducting magnets cooled, active, repelling against the coil array held it in place with a force so precise that the vehicle's actual position, measured by the sensor network, tracked the theoretical predicted position to within margins. It navigated a curve. It decelerated. It stopped safely. Every system performed. The vacuum held. The fiber optic sensors in the tube walls registered the vehicle's passage, the microscopically small deformations of the tube wall as the pressure wave of a fast-moving object swept through the sealed environment and confirmed structural integrity maintained. The AI-driven magnetic dampers, firing thousands of times per second, canceled the vibration patterns before they could grow. The test was, in the engineering team's own words, an international milestone. But here is something most people, most news reports, most excited social media posts about this story completely missed. The speed during the vacuum test was not disclosed, not because it failed, not because the results were disappointing, but because in a 2-kilometer tube, there is simply not enough distance to reach anything close to top speed. Decelerate safely and stop. The vehicle was not attempting to break speed records. It was attempting to prove the integrated system worked: navigation, levitation, vacuum integrity, emergency braking, curve, handling. All of those things, in a near vacuum, for the first time in history, they all worked, and the world barely noticed. Because the numbers 2 kilometers undisclosed speed, partial vacuum did not make for a dramatic headline, but inside the engineering community, the significance was profound. China had just done what no other country, no other company, no other engineering team in the world had ever done: validated a superconducting maglev system operating inside a vacuum tube as an integrated system, level engineering reality. Not a concept, not a white paper, not a simulation, a real test, a real vehicle, a real tube, a real vacuum. The next step had already been announced before the July test was complete: a track 60 kilometers long. On that track, the T-flight would attempt to reach 1,000 kilometers per hour, not as a stunt, not as a record, as a validation. Because 1,000 kilometers per hour, the speed of a commercial jet aircraft, reached by a train, on the ground inside a tube, is not the final destination of this technology. It is the minimum proof of concept for commercial viability. The speed at which the physics start making economic sense. The speed at which a Beijing to Shanghai journey takes 90 minutes instead of 6 hours. The speed at which Hyperloop starts to compete not with other trains, but with aviation itself. And aviation, unlike trains, burns fuel, burns it at altitude, in the upper atmosphere, where the climatic impact of each kilogram of C0 is several times greater than the same emission at ground level T. Flight, running on electricity, inside a tube, produces no direct emissions on the route. Its noise footprint, the bane of every high-speed rail line ever built, the source of planning objections, community opposition, and engineering mitigation costs across every country that has tried to build fast trains, is essentially zero. The tube contains the sound. The community above the route hears nothing. This is a transport economics story, a climate story, a geopolitical story. A story about which nation or bloc of nations controls the infrastructure of the 21st century, the way the owners of ports and railways and telegraph cables controlled the infrastructure of earlier centuries. And right now in 2024 and 2025, as Western Hyperloop companies fold and Western governments to build the country, ballistic missiles and spacecraft, is the only entity on Earth that has actually physically demonstrated that this technology works. But demonstrated is not deployed. And here is where the story shifts from achievement to ambition, from what has been proven to what must still be built. From a 2-kilometer test track in a Shanxi desert to a network that connects cities, moves millions of people, and rewrites the geography of an entire civilization. Because the hard part, the genuinely, historically hard part, was never the physics. The physics are understood. The superconductivity is understood. The vacuum dynamics are understood. The control systems, the magnetic dampers, the guideway coils, the composite tube structures, all of it understood. All of it proven. The hard part is everything else. The hard part is building 60 kilometers of vacuum tube through real terrain, through ground that is not flat, not uniform, not surveyed to the millimeter tolerance of a controlled test facility. Through ground that has drainage channels and water tables and buried utilities and zones of differential geological composition. Through ground that is owned by somebody, managed by somebody, legally encumbered, in ways that 10,000 forms and 5,000 meetings must resolve before a single beam can be laid. The hard part is building that 60-kilometer line, learning from it, and then building 600, then 6,000, then a national network. The hard part is answering the question that every serious engineer, every serious EPO maker has been asking since 2013: what does it actually cost per kilometer to build one of these things at scale? And the answer, the real answer, based on the Datong facility, based on the composite beam innovation, based on the published construction cost data, is beginning to look different from what the pessimists predicted when Virgin Hyperloop was operating. Cost estimates for their proposed systems ranged from 40 million to 100 million US dollars per kilometer. Numbers that made the economics fundamentally impossible. Numbers that made every serious infrastructure investor shake their head and walk away. The Chinese engineering team's published figures for the composite N-beam tube system suggest cost roughly 60% lower than conventional metal tube construction. That is not a marginal improvement. That is the difference between a project that cannot be funded and a project that can. Now consider what 60 kilometers of track means. 60 kilometers is not a line that connects two cities. It is a laboratory, a full-scale, real terrain, real conditions, laboratory. The largest of its kind ever built. Every meter of that track is an experiment. Every section of tube, every joint, every vacuum pumping station, every length of guideway coil installed in real-world ground conditions, rather than on the precision-prepared bed of a controlled test facility, is data. Real data. The kind of data that the entire field of Hyperloop engineering has been missing since the day Elon Musk published his white paper. The kind of data that transforms theoretical engineering into deployable infrastructure. The construction of the 60-kilometer line will begin and understand, as of the period covered in this video. The specific timeline for this phase has not been publicly confirmed in granular detail. What has been confirmed is the intent, the funding commitment from CASIC, and the engineering readiness of the team. What has been confirmed is that the target speed 1,000 kilometers per h is not aspirational language. It is an engineering specification, a number that has been calculated backwards from the physics of the system, the length of track required for acceleration and braking, and the safety margins defined by the vacuum operation protocols. Reach 1,000 kilometers per h. Sustain it. Decelerate, stop. Do it safely, do it repeatably, do it in a vacuum. That is the assignment. And the engineering of that achievement will not look like anything that has come before it. Because at 1,000 kilometers per h at this speed, you are not just dealing with the challenges of the February test or the July test. You are in a different regime entirely, a regime where things that seem like minor engineering considerations at 600 kilometers per h become dominant design constraints at 1,000. Think about the braking distance. At 623 kilometers per h, the speed of the February record, a vehicle needs substantial distance to decelerate safely. Physics does not negotiate on this point. Force equals mass times acceleration. The mass of a T-flight vehicle is fixed. The maximum deceleration you can apply is limited by the comfort of the passengers and the mechanical limits of the magnetic braking system. Do the mathematics, and the braking distance at 1,000 kilometers per h is extraordinary. It is not the kind of distance you accommodate within a 2-kilometer test track. It is barely accommodatable within a 60-kilometer line, which means the 60-kilometer line is not designed for comfort. It is designed for data. The vehicle will not reach 1,000 kilometers per h and cruise. It will accelerate to peak speed, hold it for seconds or fractions of a minute, and then immediately begin controlled deceleration. The entire run will be a single, long, perfectly choreographed acceleration, peak, deceleration sequence, every millisecond of data captured. Think about the thermal management. In a near vacuum, there is almost no medium for heat transfer. The superconducting magnets on the vehicle must be maintained at cryogenic temperatures. The MRD electronics must operate within their thermal envelopes. The guideway coils, energized to enormous field strengths to accelerate a vehicle to 1,000 kilometers per h, generate heat. In atmospheric conditions, that heat dissipates into the surrounding air. In a vacuum, it cannot. The thermal design of every component, the coil winding, the insulation materials, the cryogenic containment of the superconducting magnets, the electronics packaging, must account for the impossibility of convective cooling. This is spacecraft thermal engineering applied to a train. Think about the acoustic environment. A vehicle moving at 1,000 kilometers per h through a sealed tube. Even a tube at very low air pressure creates pressure waves. Those waves travel at the speed of sound in the partial atmosphere remaining inside the tube. If the tube geometry is not perfectly managed, if there are sections where the cross-section narrows, where the guideway geometry changes, where a branch or junction exists, those pressure waves can interact and amplify. The acoustic engineering of the tube geometry at 1,000 kilometers per h is a discipline that did not exist 5 years ago. The CASIC team are inventing it. Think about the emergency scenarios. A vehicle at 1,000 kilometers per h inside a sealed vacuum tube is in almost every practical sense unreachable by external intervention for the duration of its run. If something goes wrong, if a component fails, if a seal begins to degrade, if the vehicle develops an instability in its suspension, the response must come from within the system itself, from the AI-driven control architecture, from the magnetic dampers, from the automatic speed reduction protocols, from the emergency braking sequence that can bring the vehicle to a safe stop from any speed, at any point in the tube, without catastrophic deceleration. The emergency systems designed for the Datong tests were engineered for those tests. The emergency systems required for a 60-kilometer, 1,000-kilometer per hour validation run are a substantially more demanding specification. They must be faster, more redundant, more capable of handling scenarios that have never occurred before, because they have never been possible before. This is what the next phase of T-flight represents. Not an incremental step, not a repetition at larger scale, A genuine engineering frontier, a zone where the known unknowns are large, the unknown unknowns are larger, and the only way to discover them is to build the thing and run it. That is what China is doing. And while they do it, think about what the rest of the world is doing. In the United States, Hyperloop won. Successor entities are navigating bankruptcy proceedings and asset sales. The technology assets, the intellectual property, the engineering work of nearly a decade being auctioned, the talent dispersed, the investors nursing losses. The commercial lines that were promised Houston to Dallas, Los Angeles to San Francisco, Chicago to Columbus, not built, not started, not funded. In Europe, a patchwork of Hyperloop companies, Hard Hyperloop in the Netherlands, Nevomo in France, Swissbod in Switzerland, are conducting small-scale tests, lobbying for regulatory frameworks, and pursuing pilot projects. They are serious organizations with serious engineers, but they are years behind where China was at the beginning of 2024. The European Commission has adopted a framework for Hyperloop standardization. The regulatory vocabulary exists. The political will, in fragments, exists. The infrastructure, the kilometers of vacuum tube, the proven vehicles, the validated systems. In the United Kingdom, the situation is similar. A handful of companies, some test rigs. A regulatory environment cautiously engaging with the technology. No physical demonstration at scale. And here is the uncomfortable geopolitical reality that sits beneath all of this. India is not neutral. When Britain built railways across its empire in the 19th century, those railways moved British goods and British soldiers. They extracted resources from the colonies and delivered them to British ports. The infrastructure served power. When the United States built the interstate highway system in the 1950, as much as civilian mobility, the infrastructure served power. If China deploys vacuum tube transit at scale domestically first, and then through the Belt and Road Network, and then as an export technology to countries that cannot afford to develop their own, the infrastructure will serve Chinese economic and political influence, not through malice, simply through the logic of infrastructure. Whoever builds the trains controls the standards. Whoever sets the standards collects the licensing fees, the maintenance contracts, the supplier relationships, the data flows. This is not a paranoid reading of T-flight significance. It is the straightforward application of 200 years of infrastructure geopolitics to a 21st century technology. Most passengers, if T-flight ever becomes a commercial system they use, will not think about any of this. They will arrive at a station. They will board a vehicle. They will travel at a speed their grandparents could not have imagined. And they will not see the decade of engineering work that made the experience possible. They will not see the months of laser-guided survey work in the Shanxi desert, mapping the ground to millimeter precision before a single tube segment was placed. They will not see the development of the N-shaped composite beam, the structural innovation that cut the cost of every meter of tube by more than half and transformed the economics of the entire technology from impossible. They will not see the multi-layered joint sealing systems with their embedded pressure sensors monitoring the integrity of every connection in real time, generating alerts before failure rather than after it. They will not see the fiber optic strain gauges woven into the tube wall material at thousands of points, listening to the structural state of the entire system thousands of times, processi econdas, building a living map of the infrastructure as health. They will not see the AI-driven magnetic dampers firing their counterforces in mic huts, canceling vibrations before they can amplify into resonance that would shake the structure apart. They will not see the cryogenic cooling systems maintaining the vehicle's superconducting magnets at temperatures colder than the surface of the moon. They will not see the vacuum pumping stations installed at intervals along the tube, each one a redundant industrial system capable of compensating for the failure of its neighbors, maintaining the near vacuum environment continuously, without interruption, regardless of what is happening elsewhere in the network. They will not see the airlocks those spacecraft, great pressure transient chambers cycling through their sequences in seconds, allowing the VRGDA Fari. They will not see the engineers who spent nights running emergency scenario simulations, who argued in conference rooms about failure modes that had never occurred before, who built and rebuilt the control software until its response time to any anomaly was measured in milliseconds. They will not see the test runs, the ones where the vehicle performed nominally and the ones where it did not, and where the data from the ones that did not perform nominally was more valuable than any other data collected because it told the team, they will not see any of this. They will see a seat, a window, or perhaps no window, because a tube through which you are passing at 1,000 kilometers per HR offers no useful view. A journey time that seems impossible, a ticket price that, if the economics of the technology develop, as the engineers believe they can, will be competitive with aviation, with all the terminal time, the security queuing, the carbon footprint, the altitude effect, emissions multiplier that aviation carries with it. They will see a miracle. They will not see the 10,000 decisions that made the miracle possible, and that gap between what passengers will see and what engineers built is not a gap of transparency. It is a gap of depth. The depth that separates a technology from a system. The depth that separates a world record from a network. The depth that separates what China proved in February and July of 2024 from what the next decade must deliver. Because what was proven in 2024 is not the end of this story. It is barely the beginning. The 2-kilometer track proved the physics work. The 60-kilometer track will prove the engineering scales. After that, if the engineering scales, the question becomes whether the economics work at the level of a real corridor, a corridor connecting two cities with real passenger demand, real competing transport options, real cost structures that must eventually produce a fair revenue that exceeds the operational cost of maintaining tens of kilometers of vacuum tube at cryogenic and near vacuum conditions. Year after year, day after day, that is a harder question than the engineering. It is not a question that can be answered on a test track in Shanxi Province. But here is what the history of land infrastructure teaches us. It teaches us that the cost of new technologies always looks prohibitive until it does not. Railways in the 1840s looked economically insane until the scale of network effects and freight revenue. Aviation in the 1950s was a luxury for the wealthy until the economics of mass production and jet engine efficiency brought it within reach of ordinary travelers. Container shipping in the 1960s looked like a curiosity until it reorganized the entire global economy. In each case, the technology reached a tipping point, a moment where the scale of deployment drove down the unit cost of production, where the density of network coverage generated demand that justified further investment, where the regulatory frameworks matured and the safety records accumulated and the public perception shifted from novelty to necessity. T-Flight is not at that tipping point. It is not close to that tipping point. What it has done is prove experimentally, empirically, with published data in peer-reviewed engineering journals, that the tipping point is not physically impossible, that the technology works, that the engineering is real, that the record is legitimate in the full scope of human infrastructure history. That is not a small thing. George Medhurst imagined a pneumatic transport system in 1799. He could not build it for more than 2 centuries. The ideal lived in the space between imagination and physics, real enough to dream about, not real enough to ride. In February 2024, in a city most of the world has never heard of, in a country building infrastructure at a pace and scale that the rest of the world is still struggling to comprehend. The idea became a machine. The machine broke a world record. The machine then went inside a vacuum tube and flew. And somewhere in northern China, right now, teams of engineers are working on what comes next. Not because it is easy, not because it is cheap, not because the commercial case is certain, because the data says it is possible, because the February test says it is possible, because the July vacuum test says it is possible. And in engineering, in the long, difficult, beautiful history of human engineering, possible is where everything begins. This is not just the story of a train. It is not just the story of a record. It is the story of what happens when an idea old enough to belong to the 18th century meets the materials science, the computational power, the manufacturing precision, and the institutional will of the 21st. It is the story of a technology that failed spectacularly in the hands of the private sector, that consumed hundreds of millions of dollars, and then was taken up by a state organization with the institutional depth, the engineering heritage. It is the story of infrastructure as geopolitics, of physics as policy, of engineering as civilizational ambition. It is the story of a train that is also a spacecraft, that travels not through air, but through the absence of air, that floats 22 centimeters above its guideway on a force that operates at the boundary between classical electromagnetism, that moves at speeds which, a generation ago, belonged only to aircraft. That does all of this inside a tube buried in the ground, that you may one day, bored at a station, if you found this story as astonishing as we did, if you watched a world record fall, and a vacuum test succeed, and a 200-year-old idea finally become real, and felt what it means to live in an era when the impossible is quietly becoming the infrastructure of tomorrow, then subscribe to this channel. Because this is what we do here. We find the engineering stories that the headlines miss. We go inside the decisions that shape the structure. We follow the logic from blank desert to broken record. We stand in the gap between what passengers see and what engineers built. And we try, every video, to make that gap a little smaller. Leave a comment, tell us what you want to see next, because somewhere right now, in a desert or a mountain range or a coastline or a city that nobody has heard of yet, the next impossible thing is being built, and we will find it. Thank you for watching.